Hello. In this video, we're going to be answering the following questions. So first thing we'll answer is what is a differential equation, which we'll sometimes abbreviate as DE. Uh, Next, what does it mean to be a solution to a differential equation? And finally, we'll talk about how to classify different differential equations. This video is meant to be an intro to differential equations. So let's start off with the first question. That is, what is a differential equation? A differential equation is pretty straightforward. It's just an equation involving derivatives, as the name might indicate. So perhaps the simplest would be something like y prime is equal to, let's say, t squared, something like this. This is something that usually is not thought about as a differential equation. So the idea here is that we have a function y. So y we're thinking about as a function of t, and its derivative is given. Its derivative is t squared. Now we know from differential equations, we know from calculus 2 that the solution is 1/3 t cubed. Well, that's one solution. And of course, we know that I could add any number here, 5, 7, negative pi, whatever. So any constant here will do. We have a family of solutions indexed by this parameter. So there are infinitely many solutions. Excuse me. There are infinitely many solutions, but they all have this form. And that's just from calculus 2. So we don't normally think about this as a differential equation because it's just a simple task of integration. So let's see a slightly more involved differential equation. For instance, something like y prime is equal to y. And probably many of you know a solution to this right off the top of your heads. If nothing's coming to mind, that's okay. But what this means is that we're looking for a function, again, a function y. It could be y of t, y of x. Problem doesn't really indicate what the independent variable is, but we're looking for a function. That is the solution to this equation will be some type of function. Compare this, for instance, to an algebraic equation like x squared minus 9 is equal to 0. If we have something like this, we're looking for numbers to be our solutions. In this case, plus or minus 3 are the two solutions for this algebraic equation. But for a differential equation, the solution is an entire function, right? In some sense, an infinite amount of information. So the solution to this one turns out to be e to the t. Because if we think about it, what we're seeing is, what we're asking for is a function whose derivative gives back itself. And we know that there's one function, really one family of functions that does this. So if you objected to my saying the solution, because there are infinitely many, you're absolutely right. For instance, again, I could put a 5 here or a 7, any number would work. Let's just put a general c out in front. And we could, if we were very skeptical, we could check that y prime is just ce to the t prime, and that's ce to the t, because the derivative of ce to the t is just ce to the t, and that indeed gives us back y. So this is a solution to the equation, and it turns out every solution to this equation has this form for some constant c. Okay, so we're getting a little bit into the second question as well. What does it mean to solve? What does it mean to be a solution to a differential equation? In this case, we have a solution family. Okay, so what is a differential equation more generally? We could have some kind of wild equations. For instance, we might have something like t squared. I'll usually use t as my independent variable. T squared y double prime plus 3y times y prime, it's a plus there, not a t, equals sine of t, let's say t plus y. So this is a differential equation because it's an equation and it involves some derivatives. Now, of course, we could write this a different way. If you prefer the Leibniz notation, you could write this as second derivative in y. So we normally write it like this, plus 3 times y times dy dt. It's equal to sine of t plus y. So another way to write the same thing. The equation itself, we can generalize. So let's talk about a general definition. So definition, given a function f, and we'll just say it takes in a whole bunch of different variables, maybe something like a, b, c, dot, 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 and maybe some independent variable there, which I'll still call t. So we could have as many inputs here as you want. We might just have one input, whatever it happens to be. But a differential equation, so here we're defining what a differential equation is. And again, we often abbreviate that as just DE, is an equation of the form f of, and then we'll plug in the variables. So y, and we're really thinking about this as a function of t here, y prime of t, y double prime of t, so on. I might write, to remind you of the notation for, notice if I have 4 derivatives or something like that, it's a little bit cumbersome to write prime, 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 and if I have 72 derivatives, this becomes kind of a nightmare. So we normally put something like parentheses up here. So I'll put n for nth order derivative. So for instance, the 4th derivative would be denoted like this. And you could denote the 2nd derivative like this, but it's not very common to do that. So y to the n of t, and then finally t. This is not an equation yet. This is just plugging something in. And then that whole thing is equal to 0. Now we have an equation. You might ask, why is this equal to 0? Well, if I had something not equal to 0, I could shift everything to the left-hand side. So for instance, let's examine this top equation. We could rewrite this in the form, let's say t squared y double prime plus 3y y prime minus sine of t plus y equals 0. And then can we put it in this form? Sure, I think we just have to carefully go through and take a look at these variables, and it shouldn't be too bad. So for instance, the first entry here is y, so let's just call that variable a. Here's another a. Then we have y prime only occurs once, and y double prime we could call c, and we'll just leave t, the independent variable, as t there. So this is just some simple replacement. From here, we can rewrite this as, so the function, the associated function in this case, would be f of a, b, c, and t. And we would get something here like t squared c plus 3ab minus sine of t plus a. And our differential equation would be that this thing is equal to 0. Now, I should be clear, we almost never do this. We don't go around looking for differential equations and writing them in functional forms. This doesn't really add very much to the ideas here to write it in this way, but it's just, I just present it in this way to tell you that any differential equation, by what do we mean by a differential equation? We mean a function of a function and its derivatives, and possibly the independent variable there is equal to 0. So just to be clear, we don't have to have the independent variable. So for instance, let's see another example. If we had that one we looked at a while ago, y prime is equal to y, we could write as, let's see, so of course this would be y prime minus y. So we could write this as f of ab would be b minus a. See, so we could write it as f of ab is equal to 0, where the function would be b minus a there. In that case, y prime minus y. So that would be one way to write this equation. Of course, the function f could be written many different ways. You might express things differently. Somebody might subtract things to the left side. Someone else might do it to the right side. It doesn't really matter. The point is just that a differential equation is a function of a function and its derivatives and the independent variable. That's it. Sorry, it's not a function. It's an equation involving that function. Okay, Seem okay? That's what a differential equation is. In practice, they're pretty easy to recognize. Let's talk about a little bit more. So what does it mean to be a solution to a differential equation? And this can be deceptively simple, and is often a stumbling point for students who are getting used to this subject. So a solution. So now that we have, a definition for a differential equation, we can talk about what it means to be a solution to to the dE given by f of y of t, y prime of t, and so on, up to t is equal to 0, is just a function, y of t, making the equation true. Like I said, this is deceptively simple. This seems almost like we're saying nothing here. The solution is just something where we plug it into the equation and we get it satisfies the equation. But let's take a look at an example of where this might not be immediately obvious. So consider. So let's see an example. Consider the dE differential equation. 5y double prime plus y double prime plus 5y prime plus 6y is equal to 0. Okay, so later we'll call this a second order linear differential equation when we talk about classification. But for now, this is a differential equation, right? So for instance, we would have, I guess, f of, if we wanted to write it in this form, f of ABC. There's no t showing up explicitly. So I guess this would be c plus 5b plus 6a. And I'll stop writing these this f pretty much now. We don't really use this very much in practice, but just to verify that indeed this is a differential equation. We have something like this. Okay, so let's see what it would mean to be a solution. So first, observe, and I'm getting this, later we'll develop techniques to look at an equation like this and solve it. And you might have, if you've seen a differential equations class in undergrad, you have already seen something like this. But for now, let's just observe that e to the minus 3t is, so I should say y of t, this function equals e to the minus 3t is a solution. So this is coming from the blue at this point. We don't know why, how anyone could get this. Again, later in the course, actually quite soon, we'll see how to get these types of solutions. But for now, let's just see if somebody comes up and says, "Hey, I think this is a solution. Can we verify that it is?" So to observe that it's a solution, we have to plug it into this equation. And plugging it into that equation means, well, we put it in here. That's straightforward. But we would also have to take its derivative and its second derivative. So let's see that in action. Okay, so first let's build ourselves a chart. So y of t is e to the minus 3t, but we'll need to know the derivatives. So it looks like we only need the first and second order derivatives. So taking one derivative here, this is minus 3 e to the minus 3t by the chain rule. The next derivative here we'll get another copy of minus 3, so minus 3 squared e to the minus 3t, which is of course 9 e to the minus 3t. And we'll plug this into the equation. So we take all three of these and we plug them in. So we have y double prime plus 5y prime plus 6y. We'll substitute these in. And if we get anything other than 0, this is not a solution. If we do get 0, this is a solution. That's what it means to be a solution. Okay, so y double prime plus 5y prime plus 6y. So y double prime, you just get 9 e to the minus 3t. That's our y prime. Next, we get from the equation, from this 5, right? We get a 5 times 3e to the minus 3t. Excuse me, minus 3. And then plus 6. And then when we plug in y, we just get e to the 3t. Notice I'm being careful not to write something like that this is equal to 0, or to start over here with this thing is equal to 0 or anything like that. I don't know that it's equal to 0. We have to work out what it is. We see here that we have, let's see, so this is 9e to the minus 3t, minus 15e to the minus 3t, plus 6e to the 3t, and we have a, excuse me, e to the minus 3t, left off a minus there. And we see that we have a common factor of e to the minus 3t, and left behind is 9 minus 15 plus 6, which is, of course, just 0 times e to the minus 3t. 0 times that is 0. So indeed, this is e to the minus 3t is a solution. Okay, great. But how do we know there aren't other solutions? In fact, there are other solutions. So you can check for yourself. E to the minus 2t. So yt would be a different y of t, is also a solution. You can check that 3e to the minus 3t, maybe I'll use something like a 5 here. 5e to the minus 3t, so I should say y of t. So again, each time I'm writing y of t, I'm meaning a different y of t. Minus 5/7 e to the minus 2t is also a solution. In fact, there are infinitely many solutions. That all are of the form, some constant, we'll call it C1, e to the minus 3t, plus some other constant, e to the minus 2t, is also a solution. So all of these things are solutions. And we'll be able to prove a little bit later in the course that all solutions to that equation come in this form for different constants, C1 and C2. So this is sort of a doubly infinite family of solutions. I have free choice for C1, free choice for C2. It turns out you can even allow C1 or C2 to be complex numbers. But so long as they're constants, this is a solution, and all solutions to the equation are of this form. So all of a sudden, I think we're in a little bit of a mess here. So we just wanted to know how to solve an equation, or what it even means to be a solution. And what we found out is that first, verifying that something is a solution takes a little bit of work. It's a little bit of writing. Moreover, it's not always a unique solution, right? There may be many different solutions. So one more pretty useful exercise, and I think you should try this. Check that y of t is equal to e to the, well, let's say you could do 7t, any constant t, maybe just e to the t if you want something a little simpler. So this one is not a solution. So I encourage you to give it a try. You can use the same type of strategy here. This will be more or less the same until you'll get to a step here where those numbers don't cancel out perfectly, and then you don't get a 0 in the end, meaning that e to the 7t is not a solution. Okay, so this can be a little bit tricky sometimes to understand abstractly. So let's give that a try. So consider, again, this equation, y double prime plus 5y prime plus 6y equals 0. And suppose that we have two solutions. And we'll call them y1 of t and y2 of t. All right. Now, we don't know what these solutions are. We just saw a minute ago that there could be infinitely many solutions. Well, you should verify that those various solutions we talked about are actually solutions. But so we're just picking any two solutions. Maybe they're of a particular form, maybe not. We just have two functions here and their solutions. The question is, or the problem is, to show that a new function, y of t, which is c1 y1 of t plus c2 y2 of t, is also a solution where the c1 and c2 are constants. All right, so I've given this problem many times to many different classes, graduate students, undergraduate students, and it's normally one that, unless you've seen it before, it can be a bit of a stumbling block. And I really like the problem, though, because I think it highlights what it means to be a solution. You have to really understand that in order to solve this problem. And once you understand that, this one is a little bit of work, but it's in principle, it's not very hard to check. But it can be difficult the first time you see it. So let's do this. So first of all, we're given some information here. Let's unpack the problem. Y1 and Y2, they're not just any functions. They solve this equation. Well, what does that mean? So suppose we have two solutions, that is two solutions to that equation. What that means is that, so then, maybe I'll write in red because it's not part of the problem. We know, since they're solutions to the equation, we know that y1 double prime plus 5y1 prime plus 6y1 is equal to 0. That's what it means for y1 to be a solution, that I plug into the equation and I get 0. Notice there's nothing to calculate here. I don't know what y1 is. I mean, maybe it's an exponential, maybe it's something else. But I do know that when I plug it into the equation, I get 0. So I don't necessarily have a formula for this thing, but I can work with it abstractly. So similarly for y2, both of these things are true. That's what it means for y1 and y2 to be a solution. So what do we want to show? Want to show that y double prime plus 5y plus 5y prime plus 6y is equal to 0, where y is given by this expression. Right? Y1 is what's called a linear combination of y1 and y2. So we want to show that this is true. So let's check. All right, so y double prime, I'll start again just writing the equation. And then the idea is to work and work and work on this thing until we get 0. If we don't get 0, it's not a solution. If we do get 0, it's a solution. Well, we don't know very much about this y other than how it looks. So we'll plug it in. So first of all, I'll kind of scaffold this to have something double prime plus 5 times something prime plus 6. Notice again, I'm not writing that this is equal to 0. I don't know that it's equal to 0. Sorry, plus 6. I need some parentheses there. And what is the thing that we're going to plug in? Well, we're going to plug in y itself. Y, if I can scroll up to it, y is this green, the solution in the green box. So this looks like C1. I'll leave off the of t for convenience. So y is just C1y1 plus C2y2, C1y1 plus C2y2. I give myself a little more room. This is C1y1 plus C2y2. And at the next step, we'll use a really important fact from Calc 1, which is that derivatives are linear. That is, derivatives will distribute across addition signs, and I can pull constants out. Of course, I can do that with a second derivative by doing it twice. So here we'll get something like C1y1 double prime plus C2y2 double prime for the first bit. Then we'll get 5 times C1y1 prime plus c2 y2 prime. And the last bit doesn't change. This is just 6 times c1 y1 plus c2 y2. Now, hopefully this hasn't been too mind-blowing at this stage. We're just taking a suggestion for what a solution could be, that is c1 y1 plus c2 y2, and we're plugging it into the left-hand side of this equation. All right, but now what do we do, right? And this is a stage where a lot of students get stuck, but we have to use the things that we know. That's part of the hypothesis, right? So here, notice that we have a particular combination of derivatives of y1 add up to 0, and similarly for y2. So the idea would be maybe we can lump some of these things together. Well, here we have a y1 double prime, here we have a y prime, here we have a y, and of course this y is multiplied by 6, and y1 prime is multiplied by 5. So putting this all together, we get something like c1 y1 double prime plus c1, plus 5 times c1 y1 prime. So lumping the, collecting the y1s together, we have something like this. And then, plus I'll come to a new line, maybe I'll write it right below. This is c2 y2 double prime plus 5 c2 y2 prime plus 6 c2 y2. So it's supposed to be 1 there. And you might notice that we have some common factors here. So going on to the next line, let's factor out a c1 out of the first one and a c2 out of the second one. So this is y1 double prime plus 5 y1 prime plus 6 y1. And the next one is y2 double prime plus 5 y2 prime plus 6 y2. Okay, a little bit of writing, but hopefully the idea is straightforward. We're just grouping the y1s and the y2s and factoring out that common factor. Oh, and there's a plus here connecting those. Sorry for the multi-line equations there. But this is then, this first expression, we know because y1 is a solution, this one is equal to 0. And the second one, because y2 is a solution, this is equal to 0. So this just becomes c1 0 plus c2 0, which is 0. So check. Y itself is a solution. So this is one that I think if you master the ideas, it will be really helpful to you later in the course. I think in some sense it's an exercise that you could look at and say, well, that's pretty straightforward, but try this one on your own after you're done watching the video and see if it still makes some sense. See if you can do it on your own. That is, you have a solution, two solutions to a differential equation, a linear differential equation in this case, and what you find is that a linear combination of them is also a solution. Okay, so we've got through the first two questions. If you remember, the first one was, what is a differential equation? Second one was, what does it mean to be a solution? And we did a little bit of a deep dive on that. Next, we want to classify some differential equations. So let's talk a little bit about classification in general. Classification of, let's talk about integrands in, say, Calc 2. So in Calculus 2, you become kind of a master at seeing these different integrals and trying to use different techniques on them. So let's see some examples. If you have something like the integral of 1 over x, I think you can probably tell me this is natural log of x plus c, points for you if you remember the absolute values. So we have an antiderivative like this. Okay, no big deal. Next, though, if we change this to something like 1 plus x dx, let's maybe put just for a little bit of flavor, put 3 plus x. Then I think you can see by a u substitution, right, we would do something like, oh, u, it's equal to 3 plus x. and then du would be dx, and we could write this as integral of 1 over u du, and get that that thing is natural log of absolute value of u plus c, and that therefore would be natural log of 3 plus x plus c, something like that, right? So after a little while in Calc 2, I would say that these problems are more or less the same. If you know how to do one, you know how to do the other, so long as you're okay with u substitution. These are not fundamentally different problems. However, if instead of doing something like that, I do something like this, here I put a 3 plus, let's put an x to the 3. All of a sudden, this is a different class of problem, right? This is something like, well, we could think about this as a power rule, x to the minus 3. And then we use the old power rule trick, add 1 to the power, divide by the new power, and add a constant. So it's a bit of a different flavor. Before we got a natural log, we got another natural log when we had this, this kind of additive modification to the problem. But here, it matters, right? This somebody who was maybe just getting used to the subject might write incorrectly that this is natural log of x to the 3 by some kind of loose analogy with this way of going. And of course, that's completely wrong. In this case, this is a power function, and that's how we integrate it. All right. This gets a little more involved, just to remind you. If I do something like this, 1 over, let's say we had 1 over 1 plus x dx. Again, this is something which would give us a log. But if I square it here, all of a sudden, this is a completely different problem. And here, this is a trig substitution problem. So I'll just write trig sub. You can go review that if you want. This uses a tangent identity. Like 1 plus tangent squared is secant squared or something. But this turns out to be the arctangent of x plus c, or if you prefer, some people like to write the arctangent as tan to the minus 1 x plus c. All right, inverse tangent is better to say. So my point here is just that what's happening inside of the integrand is really important. If we make some minor changes here, all of a sudden things get a little bit wacky. And notice if I do something like 1 over 1 plus x squared, okay, we know how to integrate that. How about 2.1? Well, now we're in some trouble, right? This is all of a sudden, it's not even clear that there is any kind of Calc 2 technique to handle this thing. So it matters, right? On the other hand, of course, if I put, you know, a 2, if I kept a 2 there and a 1.1 here, no problem, right? This is it can be reduced to an arctan type thing. So it really matters what the form of the integrand is in Calc 2. And differential equations is some sense like a grown up Calc 2. We're trying to undo some derivative operations. So we really have to be careful here, right? That's a moral. We need to pay close attention. I should keep that as a 2.1. And we need to pay close attention to the form of the problem. Right, in order to solve it. And different solution techniques can yield different problem techniques, different solving techniques. So that's why we want to classify, right? So we want to be able to recognize if I'm a Calc 2 student and I'm having trouble recognizing the difference between something like this versus something like this. For instance, again, a lot of times you'll see people write incorrectly again that this is the log of 1 plus x squared, which again is dead wrong. If I'm having trouble recognizing the form of the equation, I'm not going to be able to solve I'm not going to be able to solve the problem very well. Okay, so or worse, I could apply, right, in this case, a wrong technique that just doesn't work. That's one of the biggest problems I see when students are learning a subject is applying the wrong technique to the wrong problem. So that means we should get really familiar with different types of problems. And luckily, these classifications aren't too bad. It's just kind of a way of mentally dividing up problems that have nice solution techniques, certain solution techniques, and problems where we don't really have a technique. Because, spoiler alert, it turns out that there is no general technique to solve differential equations. For certain classes, we have a general technique to solve differential equations, but differential equations in general, it's kind of like problem of solving polynomials hundreds of years ago. People just really didn't have any good solution techniques, and now we even know that for certain polynomials like fifth degree and higher, things like solution by radicals aren't even possible sometimes. So the first maybe division here. So let's talk about classification. Is linear. So the first one would be linear versus nonlinear. Some people have said that this is kind of a silly way of talking about equations because it's like calling bananas bananas and all other fruit non-banana fruit. But in this case, linear versus nonlinear, we make this division because linear problems pretty much we can solve. I have to be a little bit careful in exactly what we mean there. There are classes of linear equations which can be challenging, but for the most part, linear equations we understand very well. And nonlinear equations sometimes can be solved nicely, sometimes no one on earth knows how to solve them. There are $1 million prizes associated with solving certain nonlinear equations. So knowing this distinction is pretty important, because if we can tell whether or not an equation is linear, we have at least some hope of trying to be able to solve it. So I'm going to tell you the definition, and then I'll give you some examples. So definition. An equation, a DE, differential equation, is linear if it is in the form something like this, or maybe so something like this. Let's say a sub 0 of t, y plus, let's do a sub n of t, y with n derivatives here, plus a sub n minus 1 of t, so some function of t, then just times y n minus 1, plus, and then all the way down to something like a1 of t y prime, a 0 of t y, and that whole thing could equal some right-hand side which does not depend on t. Now, of course, it doesn't have to be of this form, so I should really say if it is in the form this or can be put in this form. So the important thing here is that the coefficients a, they're allowed to depend on t, the independent variable, but they are not allowed to depend on y in any way. So I think the best way to see this is to look at some examples, but first let's note if it cannot be put in this form, it is called nonlinear. So nonlinear is just everything else. If, let's have one more definition, if f of t is equal to 0, and by equal to 0, I mean, some people write 3 lines for identically equal to 0. So I don't just mean that it has a 0, I mean that it's equal to 0 everywhere. Then the equation is called homogeneous. So let's see an example right away of a linear homogeneous equation. So we've already seen something like this: y double prime plus 5y prime plus 6y is equal to 0. This thing is linear because it can be put in that form. There's some constant. The function here in front of y double prime is just the constantly equal to 1 function. Here's the constant 5 function and the constant 6 function. This is linear and it's homogeneous. All right, let's see another example. How about something like y double prime plus y times y prime is equal to 0. This one is nonlinear. You could say that it's homogeneous in some sense because there's no 0 here, but it turns out that the homogeneity distinction really only is helpful in the linear case. So we would normally just call this a nonlinear equation. How about that one from a little while ago? This equation. Oh, sorry about that. This equation here, you can pause and check if you like. Would this be linear or nonlinear? Right, this is nonlinear for a few reasons, right? The y is multiplied by y prime. That's not allowed in linear equations. The y itself is involved in a sine function. This is not going to work. I mean, we could have something, if we had a term there like sine t times y, this would be fine. If we had something like that in the equation, then at least wouldn't violate linearity. But the y is inside of the sine, so this is a nonlinear equation. There's no way to write the y as just multiplying by a function of t. All right, let's do something non-homogeneous, and this isn't too bad. Maybe something like y prime plus 3y. So far, that's linear, but if I put that this is equal to 7, this is linear, but it's non-homogeneous. Or we just say not homogeneous if we like. All right, or if we had something like maybe y double prime plus 3y, it's equal to sine of t. Again, this is linear, but not homogeneous. Seem okay? Because of the sine of t here. It's linear because, again, we just have a linear combination of derivatives on the left-hand side with constants out in front. Could we make it, if we had something like a t here, this is fine. This is still linear. It's okay for the independent variable to multiply the dependent variable, but we just can't have any nonlinear functions of y or its derivatives showing up. So hopefully that makes this pretty clear. And there's a worksheet in class to try a whole bunch of these. And you can find many, many examples online, people trying to classify these in different ways. Okay, next let's talk about the order of a differential equation. And this is just the highest order derivative. Occurring in the DE. So let's take a look at this. We can go back to these. Here we've got the highest order derivative is a second order derivative. So this would be a second order. This one, again, second order. And let's see, this one, so maybe we should write that this one is first order. And the second one is second order, so it's linear, non-homogeneous, but second order. Here's a little bit of a trick question for you. If I have something like y double prime squared plus y is equal to 0, what order equation should this be? And of course, I'm trying to trip you up here a little bit. This is a second order squared, so should this be a fourth order? Well, no, because it's this just means y double prime times y double prime plus y is equal to 0. The highest order derivative here is the second order derivative, right? So this is second order. And of course, it's nonlinear. All right. Okay. Now notice we sometimes have a t showing up, sometimes we do not. So let's have a definition. dE, differential equation, without the independent variable occurring is called autonomous. That is, it just autonomous, right? It just refers, it's only referring to itself. So let's see some examples here. Well, maybe we can go back here for a minute. These here, no independent variable showing up. So that's, these are autonomous. This one is not autonomous because of the t showing up. And these other three are autonomous. Let's see another example. How about something like dp dt? So this is one we'll actually look at in class, is r times p times 1 minus p. This is sometimes called the logistic equation. And here where r is constant. It's a constant. So this is a problem that comes up in population dynamics. So that's what the p is there for. Here we do see a t because we've written this out. I mean, we could have written this as p prime, but we chose to write it as dp dt. This one, well, should it be autonomous or not? The classification that we use here is that this is still autonomous. Because the t is really only showing up as a derivative. Again, we could replace that by a p prime, and we would not see the independent variable showing up anywhere. Of course, if this r, which is a growth rate, was not a constant, but maybe was a function of t or something like this, this would be a non-autonomous equation. In this case, we have that p is multiplied by 1 minus p. If you wrote that, if you multiplied those out, you would have something like p minus p squared. It's a nonlinear function, so this is a nonlinear equation, nonlinear differential equation. And the highest order derivative occurring is the first derivative, so first order. There we go. So that is some basic ideas behind classification. Sometimes for autonomous, especially in the case of a linear equation, we talk about having constant coefficients. So maybe we should write that down. So one more definition, a linear autonomous equation is said to have constant coefficients. So, so let's see an example there. If we had something like y double prime plus 5y prime plus 6y. Before we were looking at this and setting it equal to 0. Now let's put it equal to sine of t. So this is actually I should be a little bit careful here. Technically, this would be called autonomous. Excuse me. This is not autonomous. A linear equation said to have constant coefficients if a(n) t through all the way up through a0 of t, excuse me, a0 of t are constant. Excuse me. I was trying to save some space there and said something that's incorrect. So this is an example of an equation, which has, so first of all, it's linear. Maybe put these in red. Linear second order. Right? It's linear because the y's are just occurring in the standard way of in a linear equation. They're just we just have the linear combination of of y and its derivatives. So this is a linear second order equation. It's non-homogeneous, and in particular, this makes it non-autonomous. But it does have constant coefficients. So again, the reason why we do this, I mean, a pretty reasonable question here would be, who cares about this classification? Differential equations is really not a business of trying to classify a whole bunch of different things. Classification is just a helpful guide sometimes. So for instance, if you know you have an equation, which is a linear second order non-homogeneous equation with constant coefficients, that means some very straightforward techniques can be used to solve this equation. If the equation is higher order, but still is linear, non-homogeneous, and has constant coefficients, usually the same techniques can be used. If it's doesn't have constant coefficients, you still have some hope of solving the thing, but your techniques are going to change a little bit. I'm sorry to be a little bit mysterious about what these techniques are. We'll learn those in the next video. At least some of the techniques. If the equation is non-homogeneous, the techniques for these things work, but sometimes there's an additional modification that's needed. And then if the equation is no longer linear, it can be very hard sometimes to find any technique that will work. There are some techniques that do work. There are some techniques that work in special situations, but there's no general technique for solving a nonlinear differential equation. Okay, thank you very much for your attention.